Hi, and welcome to this course on decision trees for classification and regression. Decision trees fall under the category of supervised learning algorithms with nonlinear models. In the same category, we also have k-nearest neighbors, random forests, and gradient-boosted machines. Decision trees are among the most used machine learning models because of their ease of implementation and simple interpretations. The goal is actually to create a model that predicts the value of a target variable by learning simple decision rules inferred from the data features. We actually use decision trees every day in our lives when making decisions, even though we may be not realizing it. For example, when planning commute times and routes to work, we build flowchart-like tree structures in our head to conclude to the best possible solution for this given problem. Or when figuring out the best time to take a lunch break. Which campaign should I run to promote this or that item? When buying a home, should I go for a used one or not? Or in the example that we are going to illustrate over the next two slides, should I accept a new job offer or not? Let's take a look at the structure of a decision tree used in machine learning. Each tree has the following elements: a root node, decision nodes, branches, and leaf nodes. A decision tree is a flowchart-like tree structure where each internal node denotes a test on an attribute, each branch represents an outcome of the test, and each leaf node or otherwise terminal node holds a class label. In this example, we can clearly see how the decision tree branches out from top to bottom. Starting at the top, the first decision node, which is also the root node, tests against the attribute whether or not the salary is at least $50,000. Depending on the answer, the tree branches out into the yes branch or the no branch. If the answer is no, we will decline the offer and land into the first pure leaf or terminal node in green on the top right. If it's a yes, we land on a further decision node. From there, we test against the next attribute, namely, do we need more than an hour to commute to work? Similarly, if the answer is yes, we decline the offer and land into the second leaf node in the middle of the illustration. In the case of a no, we progress to the next and final decision node. There, we test against the attribute of free coffee at the workplace. If no, we decline. If yes, we accept. After all, coffee is a must. Decision trees are highly versatile predictive models. They can handle high-dimensional data with very good accuracy. They are a non-parametric supervised learning method used for classification and regression, and by non-parametric we mean that the algorithm makes little or no assumptions at all about the distribution of the data. Algorithms that don't make strong assumptions about the form of the mapping function are called non-parametric machine learning algorithms. By not making assumptions, they are free to learn any functional form from the training data. Compare this, for example, to a linear regression where the model assumes a linear relationship between the variables. Assumptions can greatly simplify the learning process, but can also limit what can be learned. Algorithms that simplify the function to a known form are called parametric machine learning algorithms. So let's learn more about decision trees by creating one using scikit-learn. For this, we'll use the example of customer churn to explore binary classification using a decision tree. And by churn, we mean if someone stops, leaves, or quits a service. We'll use, in particular, the telco customer churn dataset. So in this dataset, each row represents a customer and each column contains customers' attributes. In particular, we have information on customers who left within the last month, services that each customer is signed up for, customer account information, and demographic info about customers. When analyzing our dataset, we can see that there are 7,032 rows and 18 columns in total. As we already mentioned, each row represents a customer. The last column, churn, is whether or not a customer churned. This is our target or dependent variable. 0 would be a no and 1 is a yes. So this means that there are 17 features or independent variables. We start by importing the decision tree classifier and the train test split method. We then create a copy of our data frame, as we are going to use this one to create our data and labels. We use the train test split method to split our data into train and test sets, where the train set will contain 70% of our data points and the test set the remaining 30%. We then build our classifier. Note that we are using a max depth setting of 3. The hyperparameter max depth controls the overall complexity of a decision tree. This hyperparameter allows us to get a trade-off between an underfitted and overfitted model. We continue with fitting on the training data and labels, and finally, we make predictions on the test set. When running the classification report and confusion matrix from sklearn, we get the illustrated results. We can clearly see that for the churn class, we have a lot of false negatives, which leads to a very poor recall score and subsequently to a low F1 score. The overall accuracy of the model may look a little bit better, but don't forget that our data points are very unevenly split among the two classes. Out of the total 2100 points roughly, only 546 represent the churned class. It is crucial that we pay attention to a metric that can tell us how the model is performing overall. So how does the decision tree algorithm work? How do we build our model? As usual, we split our data into train and test sets. In this particular example, we use scikit-learn to instantiate the classifier and fit it on the training data. But what really happens under the hood? The illustrated diagram gives us a first glimpse and intuition behind the decision tree classifier's mechanics. Key here is for the classifier to select the best attributes to use in order to split the data into smaller subsets. For this, the algorithm uses one of several attribute selection measure techniques such as information gain or Gini index. More on this in the following slides. This happens recursively for every child node that is still not pure enough. Note that child node purity is a relative concept and will depend on hyperparameter tuning. Once the model is fit, we evaluate on our test set and measure its performance by means of classic evaluation metrics such as accuracy, precision, recall, and F1 score. So, how does a decision tree split our data, breaking it down into smaller subsets and ideally concluding into pure leaf nodes? The model will choose a split that maximizes the information gain. So this is based on information theory. It will use entropy to measure impurity or uncertainty, and the higher the impurity, the higher the entropy will be. In a nutshell, entropy is the measure of information contained in a state. As a result, the model compares every possible split and takes the one that maximizes information gain. The model traverses through every possible feature and feature value to search for the best feature and the corresponding threshold. Keep in mind that decision trees are greedy algorithms, so there is no backtracking and changing of previous splits. As a result, all following splits depend on the previous one. There is no guarantee of optimal set of splits, but greedy search makes our training a lot faster. Information gain, the new information you gain through splitting, is the impurity of the parent node minus the combined impurities of the children nodes. Maximizing the information gain for each split is the key for growing a decision tree. Either entropy or Gini index can be used to calculate the impurity for information gain. In this example, we see that mixed leaf nodes, the ones on the right, result in higher entropy, thus in lower information gain. Clearly, the algorithm would prefer the left split, since the combination of the chosen feature and the splitting threshold result in very pure leaf nodes, in other words, zero entropy. Summing up, in our example, choosing the best possible split translates into the algorithm asking the best possible question, the one that results in the highest information gain. Some of the hyperparameters that need to be optimized include the following: max depth, which reduces the maximum depth of the tree; min sample split, which is the minimum number of samples a node must have before it can be split; min samples leaf is the minimum number of samples a leaf must have; min weight fraction leaf is the same as min samples leaf but expressed as a fraction of the total number of weighted instances; max leaf nodes is the maximum number of leaf nodes a tree can have, and finally max features, which is the number of features to consider when looking for the best possible split. Scikit-learn has a decision tree algorithm that also works for regression problems. Most hyperparameters remain the same. The main notable difference is the criterion parameter. For regression problems, the default criterion, among several, is the squared error, which stands for the mean squared error, or MSE. Its function is to measure the quality of a split. It is equal to variance reduction as a feature selection criterion, and it minimizes the L2 loss using the mean of each terminal node. In this coding example, we start by importing the decision tree regression, the MSE metric, and the train test split method. We split our data into train and test sets. We build our classifier, and again, we are using a max depth setting of 3. As noted earlier, this hyperparameter controls the overall complexity of a decision tree. It allows us to get a trade-off between an underfitted and overfitted model. We then continue with fitting on the training data and labels. We make predictions on the test set, and finally, we compute the mean squared error. In this slide, we can clearly see how max depth controls the overall complexity of a decision tree regressor. With a setting of 5, we are clearly overfitting to almost every single data point in our set. The model becomes too susceptible to noise, which can lead to poor performance when trying to generalize on unseen data. On the other hand, reducing this hyperparameter helps us control the overfitting phenomenon, but may also lead to underfitting if the model oversimplifies the assumptions it makes about the distribution of our data. Clearly, there is a trade-off between bias and variance, and we need to spot it. Finally, some pros and cons of the decision tree algorithm. It's very easy to visualize, it's possible to deal with qualitative variables, it mirrors human thinking and decision making, and it also boosts a hierarchy of decisions. On the downside, it's not as accurate as other methods, especially if you only use a single tree. Small changes in your data can change your tree structure, and finally, it's very prone to overfitting.